If Earth were the size of a nickel, Neptune would be about as big as a baseball, but something far larger may be hiding beyond it. Not Pluto. Pluto has been demoted. This is something else. A world with 10 times the mass of our planet. It drifts so far from the Sun that a single orbit takes 20,000 Earth years. We have never seen it, but something is tilting our entire solar system by 6 degrees. Something is herding the frozen objects at the edge of our cosmic neighborhood into orbits that should not exist by chance. The odds of those orbits aligning randomly are 0.007%, and if a hidden giant lurks in our own backyard, what waits in the darkness beyond? The universe is already answering. It has shown us worlds where glass rains sideways at 5,400 miles per hour, planets stretched into the shape of lemons as they orbit the corpses of dead stars, places so hot that rock itself boils into the atmosphere. We thought we understood how planets form. We were wrong. If you enjoy what comes next, consider liking and subscribing. We begin now. Let me tell you about the layout of our solar system. Mercury sits closest to the Sun, then Venus, then us. Mars comes next, followed by the giant planets: Jupiter, Saturn, Uranus, Neptune. 8 worlds, all accounted for. Now, I know back in school you probably learned there were 9 planets, but forget about Pluto. It's been demoted. Sorry. What I'm talking about is something far more massive. Actually, let me be clear. Pluto's not even close. We're talking about a planet that makes Pluto look like a pebble, a hypothetical giant hiding in the dark edges of our solar system. In 2016, researchers at Caltech published a study that changed everything. They weren't chasing fairy tales. These were serious astronomers looking at serious data, and what they found demanded an explanation. The math pointed to something out there, something big, something real. This proposed world sits 20 to 30 times farther from the Sun than Neptune. Neptune already feels impossibly remote. Light from the Sun takes 4 hours to reach it, but this hidden planet drifts in a region so distant that sunlight barely registers as a dim star. Imagine placing a coin on a sheet of paper. You're not touching it. Nobody is. Then suddenly, the coin starts to move. It slides across the paper as if pushed by an invisible hand. You can't see anything moving it, but you know something must be there. Maybe someone underneath the table, running a magnet you can't see. That's what astronomers are dealing with. They observe the coin moving. They calculate the force required. They trace the trajectory back to its source, and they find nothing but darkness. But the coin keeps moving. Here's where it gets strange. We've been searching for this planet for years. We have powerful telescopes that can see galaxies billions of light years away. We've photographed black holes. We've mapped the cosmic background radiation from the beginning of time itself. So why can't we find a planet in our own solar system? The answer isn't that our telescopes are too weak. The answer is that we've been using the wrong kind of light entirely. Think about how you see the moon at night. The moon doesn't glow on its own. It reflects sunlight back to your eyes. That's called visible light. It's the same way we spot Mars, or Jupiter, or any of the planets we've known for centuries. We see them because they shine with borrowed light from the Sun. At the distance where this hypothetical giant orbits, visible light fails us completely. Neptune, our most distant known planet, reflects enough sunlight for our instruments to detect, but this hidden world would be 10,000 times fainter than Neptune in visible light. 10,000 times. That's not slightly harder to see. That's essentially invisible. Here's the key insight that changed everything. Searching for this planet in visible light is like looking for a black cat in a coal mine at midnight. You're straining your eyes into absolute darkness, hoping to catch a glimpse of something that simply won't reflect enough light to see. But what if you stopped looking for reflected light altogether? What if you felt around for something warm instead? Every object with mass radiates heat, even cold objects. A planet drifting in the outer solar system would still retain some internal warmth, radioactive decay in its core, leftover heat from its formation. This thermal energy escapes as infrared radiation, not visible light. Heat. In infrared light, this hidden planet would only be 100 times fainter than Neptune, not 10,000 times, 100 times. That's still dim, but it's the difference between impossible and merely difficult. The universe had been giving us signals all along. We just weren't tuned to the right frequency. There's more evidence. Not just missing planets, but unexplained physics right here in our cosmic backyard. Look at the orbits of the 8 known planets. Draw a line through their paths around the Sun. That line should align perfectly with the Sun's equator. The Sun spins, and the planets should orbit in that same plane. They don't. The entire orbital plane tilts 6 degrees away from where it should be. 6 degrees might sound small. It's not. It's like finding that your floor isn't quite level, that your entire house sits at an angle nobody can explain. The best theory we have? A massive unseen planet pulling on everything, warping the geometry of our solar system across billions of years. Its gravity doesn't need to be dramatic. It just needs to be patient. A slight tug, repeated across millions of orbits, adds up. It compounds. It tilts an entire family of worlds. This isn't wishful thinking from amateur stargazers. This is physics demanding that something explain the observations. The numbers don't work without it. Imagine an object with a mass roughly equivalent to a small version of Neptune, orbiting so slowly that a single lap around the Sun takes longer than human civilization has existed. It would complete one orbit while empires rise and fall, while ice ages come and go, while our species forgets and rediscovers fire. And the whole time, we wouldn't see it. Not because it's too small, not because it's too far, because we were searching with the wrong eyes. If infrared is the answer, then why haven't we found it yet? The question hangs in the dark. If infrared is the key, why hasn't anyone found this planet yet? The answer involves something unexpected. Scientists aren't pointing a fresh telescope at the sky and waiting for a hotspot to appear. They're digging through archives, old data, decades-old data, the kind stored on magnetic tape in climate-controlled rooms. In 1983, NASA launched a satellite called IRAS, the Infrared Astronomical Survey. It spent 10 months scanning the entire sky, cataloging heat sources across the cosmos. At the time, nobody was hunting for hidden planets in our own solar system. They were mapping distant galaxies, newborn stars, clouds of interstellar dust. The mission ended. The data went into storage. Then, between 2006 and 2011, Japan's Akari satellite performed its own infrared survey. Different technology, different era, same sky. Here's where it gets clever. If you compare what IRAS saw in 1983 to what Akari recorded over 2 decades later, anything that moved stands out. Stars don't wander. Galaxies don't drift across our field of view in 23 years. But a planet would. A planet orbiting our Sun, even one impossibly far away, would shift position between those 2 surveys. That's a 23-year gap, almost a quarter century of potential movement captured in 2 frozen snapshots. The search is like switching from looking for a candle flame to feeling for a warm radiator in a dark room. The radiator is easier to find, but you still need to map out the entire room first. And this room contains millions of heat sources. Think about what that means. Researchers aren't waiting for new observations. They're using data from a satellite launched when rotary phones were still common, when the internet didn't exist for ordinary people, when the space shuttle was brand new. 40-year-old observations might contain evidence of something we've never seen. It was there in the data all along, possibly waiting for someone to ask the right question. The teams combing through these archives have found something. 13 possible matches. 13 points of light that appear in both surveys but seem to have shifted position. 13 candidates that might be the planet everyone is hunting for. Might be. That word carries enormous weight here. Current estimates place this hypothetical world somewhere between 500 and 700 times farther from the Sun than Earth sits. At that distance, a single orbit takes so long that even across 23 years, the movement would be tiny. A speck drifting across a field of millions of specks. The mass estimates have narrowed too, somewhere between 7 and 17 times Earth's mass. Smaller than the original predictions. Still substantial enough to pull on distant objects, but confirming any of those 13 candidates is maddening. And the reason involves something you can demonstrate right now, wherever you are. Hold up your finger at arm's length, close one eye. Look at where your finger sits against whatever's behind it. The wall, the ceiling, the darkness. Keep your finger perfectly still. Switch eyes. Your finger jumped. It moved, except it didn't. You moved. Your viewing angle shifted, and that made everything appear to slide. That's parallax. Nearby objects appear to shift position when you look at them from different angles. Earth doesn't stay in one place. It orbits the sun. So when IRAS took its measurements, Earth sat at one point in its orbit. When Akari looked at the same patch of sky years later, Earth had moved to countless different positions during that survey. Every observation comes from a slightly different angle. Every angle makes nearby objects appear to shift. Imagine trying to track something moving incredibly slowly across a 23-year gap while accounting for that apparent jump. The planet itself might have crawled only a fraction of a degree across the sky. Meanwhile, the parallax effect creates its own illusion of movement. Separating real motion from apparent motion requires knowing exactly where something is. And if you knew exactly where it was, you'd have already found it. The data isn't clean. It's noisy, smeared, riddled with artifacts from aging instruments. Each of those 13 candidates might be real. Each might be a ghost, a glitch, a background galaxy that coincidentally lined up in a way that mimics planetary motion. This is why confirmation matters. Finding a candidate is the first step. Proving that candidate is genuinely orbiting our sun requires follow-up observations, repeated measurements, tracking its position over months or years with modern instruments precise enough to distinguish authentic drift from cosmic noise. The tools exist for this, or rather, they will soon. An observatory is under construction in Chile right now, the Vera Rubin Observatory. When it begins operations, it will survey the entire visible sky every few nights. Not once, repeatedly, systematically. Any object that moves will leave a trail through the data. If one of those 13 candidates is real, if something genuinely lurks at the edge of our solar system, radiating just enough warmth to detect, the Vera Rubin Observatory will find it moving. Not in archival snapshots separated by decades, in real time. Night after night after night. The limitations today are genuine. The technology from the 1980s wasn't designed for this hunt. The Japanese satellite that followed wasn't either. Both were repurposed, their data squeezed for answers they were never built to provide. And yet, those imperfect archives remain our best current hope. The fact that scientists are poring over 40-year-old infrared catalogs searching for a world that might reshape our understanding of the solar system is either humbling or remarkable. Perhaps both. The planet, if it exists, has been there the entire time. Through every survey, through every advancement in telescope technology, through every argument about whether it's real. We've been photographing this region of space for decades. The answer might already exist in data sitting on servers right now, waiting. But knowing a planet is somewhere in the outer dark and knowing exactly where it orbits are different problems entirely. One requires evidence, the other requires patience. The search continues. 13 candidates, 23 years of drift, millions of heat signatures to eliminate. Somewhere beyond Neptune, beyond the familiar worlds we've named and mapped, something massive may be completing its impossibly slow circuit around our star. If we can find hidden planets in our own cosmic backyard using archived data and mathematical persistence, the question becomes larger. What else waits in the darkness between stars? What might we find when we turn these same techniques outward, towards systems we've only glimpsed from unimaginable distances? We have been looking inward, searching our own backyard for a planet that refuses to reveal itself. But the universe extends far beyond the edge of our solar system. And out there, in the cold between stars, nature builds worlds that should not exist. If something as strange as a hidden giant can lurk in our own celestial neighborhood, what impossible things might be circling distant suns? The answer is stranger than anything we imagined. Nature doesn't limit itself to making copies of Earth. It creates planets in environments where traditional physics says planets have no business surviving. Consider what happens when a world tries to form around not one star, but two. 446 light-years from here, a planet exists that defies everything we thought we knew about planetary formation. This world has 6 times the mass of Jupiter. That makes it enormous, a true heavyweight among planets. But the remarkable part isn't its size. The remarkable part is its address. This planet orbits a pair of stars that circle each other. The 2 suns complete their mutual dance once every 18 Earth days. While they spin around their common center of gravity, the planet traces its own path around both of them. One complete orbit takes 300 Earth years. A human lifetime would pass before this world returned to where it started. The gravitational environment inside this system is chaos. 2 massive stars yanking space around them like a cosmic washing machine on spin cycle. The gravity field shifts constantly, pulling in different directions, tugging and releasing, creating zones of instability where orbits should decay and matter should scatter. According to traditional formation models, this arrangement should tear itself apart. The competing gravitational forces should have shredded any accumulating material long before it could become a planet. Young planetary systems are already fragile. Add a second star stirring the gravitational pot, and the math says nothing solid should survive. The universe is not calm, orderly, or safe, yet this planet exists. It hangs there, completing its impossibly slow orbit through gravitational turbulence that should have destroyed it. The system is only 13 million years old. In cosmic terms, that's practically newborn. The Earth took billions of years to become what it is. This world formed in a fraction of that time, in conditions that should have prevented formation entirely. The planet somehow survives this chaotic churning, like a cork that refuses to sink no matter how violently you stir the water. Something about its orbit, its mass, its precise position relative to both stars allows it to persist, where equations predict annihilation. We don't fully understand how. That's part of what makes it remarkable. The models say one thing, reality says another, and when observations contradict predictions, the predictions have to change. But binary star planets aren't the strangest survivors in the cosmic zoo. For true impossibility, we need to look at what orbits the corpses of massive stars. We need to look at pulsars. A pulsar is what remains after a star many times more massive than our sun exhausts its fuel and dies violently. The core collapses. The outer layers explode outward in a supernova, one of the most energetic events in the known universe. What's left behind is a neutron star, a ball of matter so dense that a teaspoon would weigh billions of tons. Pulsars spin rapidly and emit beams of radiation from their magnetic poles. We detect them as rhythmic pulses of energy, but here's what should be impossible. Some pulsars have planets. Think about that for a moment. A supernova is not a gentle event. It's the explosive death of a star. The blast wave races outward at significant fractions of the speed of light. Temperatures spike to billions of degrees. Radiation floods the surrounding space. Any planet orbiting the dying star should have been vaporized, scattered, reduced to nothing but expanding gas. Yet planets exist around pulsars anyway. One such world has been stretched into a lemon shape by extreme tidal forces. The gravitational pull from its dead stellar parent is so intense, so uneven, that the planet cannot maintain a spherical form. Gravity has become a sculptor, stretching and squeezing rock and metal like taffy until the world no longer resembles anything we would recognize as a planet. Its atmosphere consists entirely of helium and pure carbon, zero water, zero oxygen, nothing that could support life as we understand it. This is a world of extremes that exist beyond our everyday experience, a place where the rules of planetary formation have been rewritten by violence and survival. The existence of these pulsar planets presents a profound puzzle. Either they survived the supernova that created the pulsar, which seems nearly impossible given the energies involved, or they formed afterward, coalescing from the debris and wreckage left behind by the explosion. Both possibilities are extraordinary, surviving an apocalypse that should have erased you from existence, or being born from the ashes of stellar death. Either way, these worlds represent something remarkable: persistence in the face of cosmic destruction. Some scientists aren't even certain these pulsar objects are true planets at all. They might be the shredded cores of stars that once orbited the pulsar's progenitor, companions that were stripped and twisted and compressed by gravitational forces until they became something new, something that looks like a planet but carries the genetic memory of a star. The distinction matters. It changes what we understand about planetary formation, about what counts as a world, about where the boundaries lie between stars and planets, and the strange objects that exist somewhere in between. Then there are the red dwarf systems, where distance loses all meaning. In some tightly packed arrangements around these dim red stars, planets orbit at distances that seem absurd, less than 2 million miles from their parent star. For comparison, our moon sits roughly 240,000 miles from Earth. These planets orbit their stars at distances only a handful of times greater than the gap between us and our own moon. At such proximity, the year shrinks to almost nothing. Some of these worlds complete their orbits in just 2 Earth days. Others take 3.5. While you work through a typical week, these planets have circled their star twice. The gravitational grip at these distances is intense. Many of these worlds are likely tidally locked, meaning the same face always points toward the star. One hemisphere burns in perpetual daylight, the other freezes in endless night. The boundary between them would be a strip of eternal twilight, where shadows never move, and the star hangs forever on the horizon. These are not gentle environments. These are not places where liquid water pools quietly in crater basins. These are worlds shaped by proximity, by tidal stress, by radiation bombardment at ranges we associate with satellites, not planets. And still, they exist. Every impossible world we find expands our understanding of what nature permits. Binary planets that should have scattered, pulsar planets that should have vaporized, tight orbit worlds that should have spiraled into their stars long ago. They all persist. They all orbit. They all challenge the tidy models we constructed from studying our own relatively calm solar system. We grew up thinking planets needed space, room to form, stable orbits around single, well-behaved stars. We thought the environment mattered, that certain conditions were prerequisites for worlds to coalesce from dust and gas and become something solid. The universe has been teaching us otherwise. Every survey that points toward distant stars returns data that shouldn't make sense, planets where planets shouldn't be, survivors of events that should have been unsurvivable, shapes that shouldn't exist, atmospheres that shouldn't persist, orbits that shouldn't remain stable. The patterns we expected to find aren't there. Instead, we find variation, creativity, a universe that builds worlds according to rules we're only beginning to decipher. If gravity alone could destroy a planet, some of these worlds would be gone. But gravity isn't the only force acting on distant worlds, and survival isn't just about where you orbit. It's about what your star does to you while you hang there in the dark. The universe builds what it wants, where it wants. We've seen that now. Planets orbiting the corpses of collapsed stars, worlds tucked so close to their suns that a single week contains multiple years, systems that should have torn themselves apart billions of years ago, still spinning, still intact. But we left something unfinished. Planet 9, the mysterious Waldo from space. We know roughly what to look for. We know roughly where to look. The problem is that the cosmic version of finding Waldo involves a search area so vast that our minds refuse to process it. This isn't a children's book with 100 cartoon figures on a beach. This is a canvas stretched across billions upon billions of cubic miles of empty space, and somewhere in that darkness floats a single object we've never directly seen. Here's what makes the infrared approach different from everything astronomers tried before. When you search for a planet in visible light, you're looking for reflected sunlight. The planet has to catch some rays from the sun and bounce them back toward us. At the distances we're talking about, that reflection becomes almost nothing. Neptune, the farthest confirmed planet, sits far enough out that light takes roughly 4 hours to reach it from the sun. Planet 9 sits perhaps 15 to 20 times farther than that. By the time sunlight reaches that distance, spreads across space, bounces off whatever surface exists there, and travels all the way back to our telescopes. The signal has faded into statistical noise, but infrared works differently. Everything with mass radiates heat. Even something frozen by any human standard still glows in wavelengths our eyes cannot see. A block of ice in your freezer emits infrared radiation. So does the deepest cave on Earth. So does a planet drifting through the outer reaches of a solar system, slowly leaking the primordial warmth it collected during its formation. The difference is staggering. In visible light, hunting Planet 9 means looking for something that has essentially disappeared. In infrared, the target becomes merely difficult instead of functionally invisible. That shift from impossible to difficult is everything. The 13 possible matches pulled from the historical satellite data represent a genuine breakthrough. These aren't random guesses or wishful thinking. They're points in the sky where two separate surveys, conducted decades apart, recorded something that moved in exactly the way a distant planet should move. Not a star, not a galaxy, not instrument error. Something real, something cold, something waiting. Whether this really turns out to be the Planet 9 discovery, only time will tell. The candidates need follow-up observations. They need verification from ground-based telescopes and newer orbital instruments. Science doesn't work on excitement alone. It works on repetition, confirmation, the slow accumulation of evidence until doubt becomes unreasonable. The estimated properties of Planet 9 place it in a category scientists call a big icy planet. Mass somewhere between 7 and 17 times greater than Earth. Distance from the Sun measured at 500 to 700 times the gap between Earth and our star. That's not a short drive. If you could somehow travel at the speed of a commercial airliner, the journey would take longer than our species has existed. The orbit matters too. Searching for Planet 9's path through space is like waiting for a bus that left before the pyramids were built. The ancient Egyptians stacked limestone blocks into monuments that still stand today, and somewhere out in the darkness, Planet 9 was just beginning the same orbit it's still completing now. By the time it finishes one full circuit around the Sun, 20,000 years will have passed. That's longer than all of recorded human history. Every empire, every war, every discovery, and every forgotten civilization, all of it fits inside a single lap for this distant world. The search teams have narrowed the possibilities dramatically. Early estimates suggested the planet could be almost anywhere along a massive orbital path. Current analysis points to specific regions of sky, specific distances, specific brightness ranges. The target has gone from theoretical to tangible. Here's the honest answer. We don't really know where Planet 9 came from. It might have formed with our solar system and been kicked out to the fringes by Jupiter, acting like a cosmic bully. In the early chaotic period of our solar system's history, Jupiter's gravity was throwing smaller objects around like debris in a hurricane. Some fell inward toward the Sun, some got ejected entirely, flung into interstellar space to wander forever between stars, and some, perhaps, got pushed just far enough to settle into stable but incredibly distant orbits. Or, and this is the weird part, it might not be from around here at all. It could be a rogue planet, a wanderer from interstellar space that our Sun captured. Think about that for a moment. A world that formed around a completely different star, in a completely different part of the galaxy, somehow ended up drifting close enough to our Sun that gravity reached out and grabbed it. We just don't know yet. If Planet 9 is captured, it would be an adopted child of our cosmic family rather than a sibling. It would share none of the chemical history of the other planets. Its composition might reveal elements and ratios that don't match anything else orbiting our Sun. It would be a fragment of somewhere else, incorporated into our system by chance and gravity. Both origin stories are scientifically plausible. Both fit the available data. The only way to know for certain is to find the planet itself, study its composition, analyze its orbit with precision, and let the evidence speak. The search continues on multiple fronts. Archival data from satellites that flew before smartphones existed gets re-examined with modern software. New observations target the most promising candidates. Theoretical models refine the expected orbital parameters, shrinking the search zone with each calculation. Meanwhile, every exoplanet discovery proves that the universe hides worlds in places we never expected. Planets survive binary star chaos. Planets orbit the spinning cores of dead suns. Planets exist in arrangements that violated our assumptions until observations forced us to accept them. Planet 9 would be strange, but no stranger than what we've already confirmed around distant stars. The question isn't whether such a planet could exist. The question is whether one exists here, in our own backyard, waiting to be found. The search continues, and while we wait for Planet 9 to reveal itself, astronomers keep finding worlds around other stars. Some of these discoveries sound promising at first, Earth-sized, rocky, orbiting at the right distance. Then you look closer and the dream falls apart. 150 light-years from here, there's a planet called HD 137010b. Say it out loud, and it sounds like a license plate. But the numbers behind that awkward name tell a story that almost feels too good. This world is rocky, about the size of Earth. It circles a star similar to our Sun, and it completes one orbit in roughly 1 Earth year. The same rhythm our planet has kept for over 4 billion years. When astronomers find a planet with those characteristics, they pay attention. A rocky world, a sun-like star, a familiar orbital period. That combination is rare. Most exoplanets are either too close to their stars, too far away, too massive, or too small. HD 137010b hits several checkboxes at once. Finding it required watching, waiting, and measuring something almost impossibly faint. Imagine a tiny bug crawling across a flashlight beam. The bug is the planet, the flashlight is the star, and we study the dimming of the beam as the bug passes. That's the transit method. When a planet crosses in front of its star from our perspective, it blocks a fraction of the starlight. Not much, barely anything, really. That dimming is absurdly subtle, like noticing a lighthouse flicker from across an ocean because a moth flew past it. Yet our instruments can detect it. HD 137010b announced itself through a transit lasting about 10 hours. A tiny shadow crossing a distant sun, 150 light-years away. From that brief dimming, astronomers calculated the planet's size. From the timing of repeated transits, they figured out its orbital period. From the star's characteristics, they estimated how much energy reaches the planet's surface. And that's where the promise starts to unravel. HD 137010b receives less than 1/3 of the heat and light that Earth gets from our Sun. Think about what that means. Earth sits in a sweet spot, not too hot, not too cold, the Goldilocks zone. We get exactly the right amount of solar energy to keep water liquid across most of our surface. This distant world gets a fraction of that warmth. The maximum surface temperature on HD 137010b is estimated around -90 degrees Fahrenheit. For comparison, Mars averages about -85 degrees Fahrenheit. This planet is colder than Mars. Not slightly colder, consistently colder, even at its warmest. That's not grab a jacket cold. That's your face freezes right away cold. The kind of cold where exposed skin becomes a medical emergency in minutes. On Earth, -90 would be an extreme Antarctic reading, the kind of temperature that kills exposed flesh within moments. And that's the high estimate for this world, the warmest it gets. The habitable zone calculations offer a coin flip at best. There's a 40% chance HD 137010b sits in the conservative habitable zone, the region where liquid water is most likely. A 51% chance it falls within the optimistic habitable zone, a broader definition that stretches the boundaries. Essentially, nobody knows for certain whether this planet technically qualifies as habitable or not. Picture standing on the surface, if you somehow could. The star hangs in the sky, dimmer than you'd expect, familiar in shape but stingy with its warmth. The light reaches you, but it carries less energy, like standing next to a dying campfire instead of a blazing hearth. You see the glow, but you don't feel the heat. Any water on this world would be locked in ice. Not the seasonal ice we know from polar regions, but permanent frozen sheets covering everything. Lakes would be solid. Oceans, if they ever existed, would be frozen to their depths. The surface would be a landscape of frost and stone. There's one possibility that could change the picture: atmosphere. If HD 137010b has a thick carbon dioxide atmosphere, it might trap enough heat to raise the temperature. Carbon dioxide is a powerful greenhouse gas. On Venus, a dense carbon dioxide atmosphere creates surface temperatures hot enough to melt lead. The mechanism works in reverse too. A planet receiving little heat from its star could use an atmospheric blanket to hold on to whatever warmth it gets. But this is speculation built on hope. We don't know if HD 137010b has an atmosphere at all. We don't know its composition. We don't know its density. The planet might be wrapped in gases that could warm it, or it might be barren rock exposed directly to space. The transit method tells us size and orbital period. It tells us almost nothing about atmospheric conditions. Without more data, we're guessing. And the guesses lean toward frozen wasteland rather than habitable world. This is the cruel trick exoplanet hunting plays on us. The statistics sound so promising. Earth-sized, sun-like star, year-long orbit. Every piece of the puzzle seems to fit. Then you calculate the actual energy reaching the surface, and the dream evaporates. Matching Earth's basic parameters does not mean matching Earth's conditions. We want to find another Earth so badly that we sometimes see what we hope for instead of what the numbers actually show. HD 137010b teaches humility. The universe does not arrange itself for our convenience. A planet can check every box on our wish list and still be utterly hostile to life as we know it. The transit that revealed this world lasted 10 hours. 10 hours of slightly dimmed starlight, 150 light years away. From that whisper of information, we built a picture of a frozen world orbiting a familiar-seeming star at a familiar-seeming distance. The familiarity is the trap. It makes us project our own experience onto something profoundly different. Somewhere on HD 137010b, the star rises and sets in a pattern an Earth observer would recognize. Day follows night, follows day. Seasons might cycle as the planet traces its orbit, but none of that rhythm brings warmth. The star shines, and the surface stays frozen. Not every candidate survives closer examination. Some worlds that seemed promising turn out to be cosmic illusions, their statistics hinting at habitability, while their reality sits somewhere between desolate and deadly. HD 137010b joins that list. A planet that looked like it might be somewhere special until the numbers told a different story. The search for habitable worlds continues regardless. Every frozen candidate teaches us something about what makes Earth work. Every disappointment refines our understanding of where life might actually survive. HD 137010b is not the destination, but other super-Earths wait in the darkness, orbiting other stars, and some of them might offer more than ice and silence. But other super-Earths wait in the darkness. That phrase keeps coming up. Super-Earth. We should probably talk about what that actually means. A super-Earth is not a better Earth. It is not an upgraded Earth. The name describes size, nothing more. Any planet bigger than Earth but smaller than Neptune falls into this category. Think of it as a cosmic middle child, too large to be rocky and familiar, too small to be a bloated gas giant. Somewhere in between, and the somewhere can mean almost anything. These worlds range from potential ocean planets to pressure-cooked hellscapes. The category tells you almost nothing about what you would actually find there. A super-Earth could be habitable. It could be instantly lethal. The label just tells you it sits in that middle range of planetary mass. With that vocabulary established, let us meet some of these worlds. Gliese 667. CC sits 22 light-years from Earth. That sounds close. In cosmic terms, it practically is. A neighboring star system, right next door by galactic standards. But 22 light-years converted to miles becomes a number that breaks intuition. 129 trillion miles. That is 1.4 million times the distance between Earth and the Sun. Here is another way to think about it. If you started driving toward Gliese 667 CC at highway speeds when the last ice age ended, you still would not have arrived yet. Not even close. You would have covered a fraction of the journey. The glaciers retreated. Humanity invented agriculture, cities, writing, mathematics, spaceflight, and your hypothetical car would still be crawling through the void, barely started on a trip that would take tens of thousands more ice ages to complete. That is 22 light years. That is our neighbor. Gliese 667 has 3.8 times Earth's mass, denser, heavier, with stronger gravity tugging at the surface. Its year lasts 28 days. 1 month here equals 1 complete orbit there. The planet circles a red dwarf star, part of a triple star system where 3 suns share the sky in complicated patterns. Kepler 22b sits much farther away, 600 light-years from Earth, 2.5 times our planet's size, with a year lasting 290 days. That orbit places it squarely in its star's habitable zone, the region where liquid water might exist on the surface. The planet was one of the first confirmed super-Earths in a potentially life-friendly location, but we know almost nothing about what Kepler 22b actually looks like. Is it rocky? Is it wrapped in choking gas? Does it have oceans or deserts? Or something we have never imagined? 600 light-years is too far to tell. Kepler 69c orbits even more distantly. 2,700 light-years separates us from this world, 70% larger than Earth. Its 242-day orbit places it in an orbital position uncomfortably similar to somewhere we know well, Venus. This is the part that gets me. We call it the Goldilocks zone, like it is some cozy guarantee of habitability. Not too hot, not too cold. But the universe does not care about our fairy tale. Venus is technically in the habitable zone. Look how that turned out. Venus and Earth formed from the same cosmic dust cloud. They are practically twins in size. They orbit the same star at similar distances. Everything about Venus suggests it should be Earth's closest relative, a sister world where life might flourish under familiar conditions. Instead, Venus became something monstrous. The surface temperature reaches 878 degrees Fahrenheit, hot enough to melt lead, zinc, and tin, hot enough that no probe we have ever sent survived more than a few hours. The atmosphere is 96% carbon dioxide, pressing down with 90 times Earth's atmospheric pressure. Standing at sea level on Venus would feel like being half a mile underwater, except the water is replaced by crushing, superheated gas. Clouds drift through that atmosphere. Not water clouds, sulfuric acid. The rain that falls from those clouds never reaches the ground. It evaporates in the furnace heat, rising back up to condense and fall again in an eternal cycle of corrosive precipitation. Venus is Earth's evil twin, locked in a pressure cooker with the lid welded shut. Standing on Venus would not hurt. You would not exist long enough to ever feel it. The temperature, the pressure, the acid, any one of them, would end you instantly. Together, they represent a form of planetary hostility that makes other lethal worlds look gentle by comparison. And Venus sits in the habitable zone, that zone we treat as special, that zone we search for around other stars, the Goldilocks region where liquid water should be possible, but Venus shows us what can go wrong. A runaway greenhouse effect transformed a world that might have had oceans into a vision of planetary hell. The same could happen anywhere. The same might have already happened on Kepler 69c, sitting in its Venus-like orbit around a distant star. We do not know. We cannot see through the light years to check surface conditions. All we know is orbital distance, size, and the terrible example Venus provides. TOI 733b offers a different kind of uncertainty. 245 light-years from Earth, this super-Earth might be a massive ocean world, water covering the entire surface, possibly miles deep, a planet without continents, without beaches, without dry land of any kind. But the word might is doing an enormous amount of heavy lifting in that sentence. The data suggests a low density, consistent with large amounts of water. The data also permits other interpretations. Maybe the planet is rocky with a thick atmosphere that mimics the signature of water. Maybe our instruments are picking up noise we have misread as signal. Maybe TOI 733b is something entirely different from what we have guessed. Ocean worlds capture our imagination because water means life to us. Water is where our chemistry works. A planet covered in ocean seems like a natural place to search for something swimming, growing, evolving beneath the waves. But deep oceans on super-Earths might not work the way shallow seas do on Earth. The pressure at the bottom could create exotic forms of ice that never melt despite high temperatures. The water column could suppress volcanic activity that recycles chemicals necessary for life. Too much of a good thing might be just as deadly as too little. Each of these super-Earths represents a category of mystery. Gliese 667cc, orbiting close enough that we can imagine visiting someday, but still impossibly far by any human measure. Kepler 22b, sitting pretty in a habitable zone that means less than we want it to mean. Kepler 69c, positioned where Venus stands in our own system, carrying all the warning that comparison implies. TOI 733b, potentially awash in water, or potentially something else entirely. We name them. We measure their masses and orbits. We calculate where they sit relative to their stars. We use phrases like habitable zone and Earth-like and super-Earth, words that suggest familiarity, that hint at places we might recognize. The reality is different. These remain worlds we have barely glimpsed, points of slightly dimmed starlight analyzed across distances that make our entire civilization seem like a brief flicker. We know they exist. We know approximately how big they are and where they orbit. Everything else is inference, calculation, and hope mixed in proportions that shift with every new observation. The catalogue grows longer each year. More super-Earths, more tantalizing statistics, more reasons to wonder what waits on surfaces we will never touch, beneath skies we will never see, on worlds that do not know and cannot care that something here is watching. We assume orbits are circles, clean ellipses at worst, gentle curves that carry planets around their stars in predictable paths. Earth traces a nearly perfect ring around the Sun. So do most of our neighbors. This feels normal to us. It feels like the default. It is not the default. When we look beyond our solar system, we find orbits that would terrify us. Stretched ovals that swing planets close to their stars and then fling them back into the cold. Paths so elongated they barely qualify as orbits at all. More like repeated falls toward fire followed by desperate escapes into darkness. HD 20794d shows us what this looks like in practice. This planet does not orbit in a comfortable zone. It passes through one. The difference matters more than you might think. Picture an orbit shaped like a rubber band pulled to its limit. At one end, the planet sweeps close to its star. Heat pours down. Temperatures climb. Whatever liquid might exist on the surface begins to boil. Steam rises. Oceans evaporate. The world becomes a pressure cooker with no relief valve. Then the planet swings away. The star shrinks in the sky. Distance grows. Cold returns. Not a gentle autumn chill. Not a hard winter. Something worse. The temperature drops so far, so fast, that whatever boiled away now freezes. Not just the surface. Everything. Ice forms from the ground up, locking the entire planet in a frozen shell. This cycle repeats. Over and over, year after year. The habitable zone becomes less like a cozy thermostat setting and more like a door that keeps swinging open to an oven, then slamming shut on a freezer. We use the phrase habitable zone as if it means something stable, as if sitting within it guarantees moderate temperatures and liquid water. But the zone is a snapshot. It describes a region of space, not an orbital path. A planet can be in the zone at one moment and 100 million miles outside it at another. HD 20794d does exactly this. It crosses through the zone rather than settling within it. Whatever exists on that world experiences not seasons in any sense we would recognize, but complete phase transitions of its entire environment. Summer does not mean warm afternoons and longer days. Summer means the oceans boil. Winter does not mean snow and shorter days. Winter means the atmosphere might freeze and fall from the sky. Try to imagine life surviving this, not adapting to mild variations in temperature or rainfall, adapting to your entire ocean disappearing into vapor, then reforming as a solid block of ice kilometers thick. Every organism would need to survive being boiled and frozen in the same year, not once, repeatedly, for millions of years. This is not impossible for life. We do not know enough to say impossible, but it demands a kind of resilience that makes Earth's extremophiles look pampered. Our toughest bacteria survive high heat or extreme cold. They do not routinely experience both within months of each other. The habitable zone was never a guarantee. We knew that, but we imagined planets sitting peacefully within it, circling at safe distances, maintaining steady temperatures over geological time. HD 20794d reminds us that being in the zone is meaningless if your orbit does not keep you there. How do orbits become this extreme? Gravity. Not the gravity of a single star holding a single planet, the gravity of entire systems, crowded with worlds, each pulling on every other. When multiple massive bodies share a solar system, their gravitational influences do not simply add together. They interact in complex ways that can amplify small perturbations into catastrophic changes. Consider a planet forming in a nice, circular orbit. Everything seems stable. Then a larger planet, something with serious mass, passes too close. Their gravitational fields interact. The smaller world gets tugged off course. Its orbit stretches. What was a circle becomes an oval. What was an oval becomes something more extreme. This process can repeat. Each close encounter adds energy in chaotic ways. Some planets get flung inward, their orbits tightening until they spiral into their stars. Others get thrown outward, stretching their paths into the frozen reaches of their systems. Some get ejected entirely, sent wandering between stars with no home at all. The survivors often carry scars of these encounters in their orbital shapes. HD 20794d might be such a survivor. Something big passed too close at some point in the distant past. The gravitational kick reshaped its orbit into the extreme ellipse we observe today. This is not rare. As we catalogue more exoplanets, we find extreme orbits everywhere, ellipses stretched to breaking point, paths tilted at strange angles to their systems, worlds that swing close enough to graze stellar atmospheres before retreating to distances where their stars become dim points of light. Our solar system looks orderly by comparison. 8 planets moving in nearly circular orbits, all roughly aligned in the same plane. This feels natural because it is all we knew for most of human history. But when we look outward, we see chaos preserved in orbital mechanics, the record of ancient gravitational battles written in the shapes of planetary paths. Jupiter may have protected us from this fate. Its massive gravity dominates our outer solar system, but it also cleared debris and stabilized orbits over billions of years. Without something like Jupiter, Earth might have suffered the same gravitational scattering that created HD 20794d's violent seasons. Think about what stability actually requires. A planet needs to form in the right place. It needs to avoid collision with other forming worlds. It needs to survive the gravitational influences of every massive body in its system for billions of years. One close encounter with something big enough can undo everything. We orbit peacefully because nothing disturbed us, not because peaceful orbits are common, not because the universe prefers stability. We got lucky. Our orbit remained a circle while others were twisted into stretched ovals that carry them through fire and ice in endless repetition. HD 20794d is not some exotic exception. It might be closer to the rule. When we find planets in habitable zones, we need to ask not just where they are, but where they go. The zone is a region. The orbit is a path. If the path only passes through the region rather than staying within it, all our hopeful calculations about temperature and liquid water become meaningless. The habitable zone was a useful concept. It still is. But we built assumptions into it that reality does not support. We assumed orbits would cooperate. We assumed planets would settle into comfortable distances and stay there. We assumed the zone was a place where things could live, rather than a boundary things might occasionally cross while swinging between extremes. HD 20794d teaches us otherwise. Being in the habitable zone does not matter if your orbit sends you screaming through it, rather than letting you peacefully orbit within it. The zone is a snapshot, but orbits are dynamic, and dynamic orbits, shaped by the gravitational chaos of crowded solar systems, often look nothing like the gentle circles we call home. The zone is a snapshot, the orbit is a path, but there is something worse than a bad orbit. There is heat. If gravity does not destroy a planet, heat will. 400 light-years from Earth, a world called WASP 18b circles its star so closely that it completes an entire orbit in just 23 hours. 1 day on Earth, 1 full year on WASP 18b. That is not a typo. This planet experiences a complete revolution around its sun while you sleep, wake up, and go about your day. The mass of this world is staggering. 10 times the mass of Jupiter, which itself is more than 300 times the mass of Earth. This is not a small rock skimming past its star. This is a bloated giant, swollen with mass, locked in a death spiral so tight that its atmosphere has been cooked into something we barely recognize. 5,000 degrees Fahrenheit. That is the temperature of the atmosphere on WASP 18b. For comparison, that is hotter than the surface of some smaller stars, hotter than molten steel, hotter than the melting point of every substance you have ever touched in your life. At these temperatures, water cannot exist, not as liquid, not as ice, not as vapor. The molecular bonds simply break apart. What fills that atmosphere instead? Carbon monoxide, a poison gas that forms when there is not enough oxygen to make carbon dioxide. The chemistry tells us something important. This world is not just hot, it is fundamentally hostile to water in any form. The very building blocks of oceans were either burned away or never existed here at all. WASP 18b is an extreme example, but it points toward a discovery that genuinely disappointed the scientific community. For years, astronomers hoped that a common type of planet might be our best chance for finding alien oceans, sub-Neptunes. These are worlds larger than Earth but smaller than Neptune. They exist in enormous numbers throughout the galaxy, more common than gas giants, more common than rocky Earth-sized worlds. If even a fraction of them held liquid water, the universe would be swimming with potential habitats. That hope is dying. A planet called K218b once looked promising. It showed signs of methane and carbon dioxide in its atmosphere, both gases that could suggest biological activity or at least interesting chemistry. But something was missing: ammonia. On a genuine water world with the right conditions, ammonia should appear. Its absence suggests the atmosphere is not what we hoped. The chemistry points towards something else entirely. The pattern keeps repeating. We find a sub-Neptune at a reasonable distance from its star. We get excited about the possibility of oceans. We look closer, and we discover something far less inviting. Many of these worlds are not water havens. They are magma furnaces. Picture a planet with no solid surface, no oceans, no continents, just a global sea of molten rock, glowing orange and red, stretching from horizon to horizon in every direction. The temperature at the surface sits at thousands of degrees. Rock does not just melt at these temperatures. It vaporizes. It becomes gas. These magma worlds do not have weather in any sense you would recognize. The clouds above them are not made of water droplets. They are made of vaporized stone. Silicates and metals that boiled off the surface rose into the upper atmosphere and condensed into tiny particles. And then, this vaporized rock does something that sounds impossible, but happens constantly on these worlds. It rains. Molten stone falls from the sky. Not water, not even the exotic ices we find on distant moons. Just rock, liquid rock, dripping back down from clouds of vaporized minerals to splash into the magma ocean below. This is the water cycle on a magma world. Rock evaporates. Rock condenses. Rock falls. Rock melts again. Over and over. An endless loop of geological violence masquerading as weather. Sub-Neptunes are not potential ocean paradises. They are cosmic furnaces on an assembly line, mass-produced hellscapes that shattered our dreams of finding easy water worlds. This was a genuine scientific disappointment, not because scientists are pessimists, but because the numbers looked so good. Sub-Neptunes are everywhere. If they commonly held water, finding life beyond Earth became a matter of statistics. Point enough telescopes at enough sub-Neptunes, and eventually you find something wet, something potentially alive. That comfortable assumption crumbled when the data came in. World after world revealed not oceans, but lava. Not atmospheres of water vapor, but atmospheres of vaporized stone. The most common type of planet in the galaxy turned out to be the wrong type of planet for life as we understand it. So here is the question that should keep you up at night. If the most common type of planet in the galaxy, these sub-Neptunes, are not the water worlds we hoped for, but are instead mass-produced lava furnaces, where does that leave our chances of finding life? Just sit with that for a moment. The situation gets worse for planets that orbit even closer to their stars. Ultra-short period planets. These are worlds that complete their orbits in less than a single Earth day. They circle so close to their suns that the radiation becomes overwhelming. The stellar wind, that constant stream of charged particles flowing outward from every star, begins stripping away everything. First, the outer atmosphere goes, then the deeper layers, then the gases that might once have cushioned the surface. Year after year, century after century, the star sandblasts away everything that made the planet a planet. What remains is a skeleton, a dense metallic core exposed to the void. All the lighter elements that once surrounded it have been blown away into space. Only the heaviest material survives. Lead, iron, nickel, the bones of a world that once had skin. These stripped cores are among the densest objects we have found that are not stellar remnants. They pack enormous mass into tiny volumes because everything fluffy has been removed. Every gas, every light element, every trace of atmosphere, just the compressed heart of what was once a larger body. The process takes millions of years, but the outcome is inevitable for any planet close enough. The star always wins. Heat and radiation tear away layer after layer until nothing remains but that dense metallic ball, circling endlessly through radiation that would vaporize any unprotected human in seconds. We used to think the main threat to planets was gravity, getting too close to a massive neighbor, being flung out of a solar system by a passing giant, having your orbit twisted into something unsurvivable. Those dangers are real. We have seen them. But heat is equally lethal and far more common. Most stars are not gentle like our sun. Most stars are red dwarfs, smaller and cooler, which sounds friendlier until you realize what it means. For a planet to be warm enough for liquid water around a red dwarf, it must orbit extremely close enough for the stellar wind to begin its work, close enough for tidal forces to lock one face permanently toward the star, close enough for ultraviolet radiation to bombard the surface continuously. The habitable zone around these common stars sits inside the danger zone for atmospheric stripping. Planets that might otherwise hold water get their atmospheres torn away before life could ever arise. The very proximity that provides warmth also delivers destruction. Earth orbits far enough from our sun that the solar wind barely touches us. Our magnetic field deflects what does arrive. Our atmosphere remains intact across billions of years. We take this for granted because we have never known anything else, but most planets in the universe do not share this protection. Most planets either freeze in darkness far from their stars or bake in radiation close enough to feel warmth. The narrow band where liquid water can persist without being stripped away is smaller than we once believed. The cosmic furnaces keep burning. Sub-Neptunes with their magma oceans and rock vapor atmospheres. Ultra-short period planets with their exposed metallic cores. Hot Jupiters like WASP-18b with their carbon monoxide skies and temperatures that rival small stars. And somewhere beyond them, in the coldest regions of our own solar system, something massive continues its slow orbit through darkness. Something that might explain the strange alignments we see at the edge of the known. After all that cosmic horror, let us come back home. Our own solar system has a secret, something hiding in the dark, cold reaches where sunlight fades to almost nothing. We have spent these past moments wandering through alien nightmares, worlds where glass falls sideways, planets stripped down to their metallic bones, stars that destroy everything that dares orbit too close. But the strangest mystery might be right here, in our own backyard, 2.5 billion miles from the sun, beyond the familiar planets, beyond the comfortable warmth that makes Earth possible. There exists a region called the Kuiper Belt. It is shaped like a donut, a vast ring of frozen debris left over from the formation of our solar system. Chunks of ice and rock that never became planets, the forgotten scraps from the cosmic kitchen. Most of these objects drift quietly in the darkness. They follow the rules. Their orbits lie relatively flat, aligned with the plane where the planets travel, just as you would expect from debris left behind by a spinning disk of gas and dust. Random, yes, but predictable in their randomness, except for 6 of them. The 6 farthest objects we have found in the Kuiper Belt behave strangely. Their orbits tilt downward, away from the expected plane, 30 degrees down. All of them, all tilted the same direction, all pointing toward the same region of empty space. Consider what this means. Picture papers scattered across a desk, dozens of them, maybe hundreds, lying flat in random orientations. Some face left, some face right, some diagonal. The randomness makes sense. That is what happens when papers are scattered. But the 6 papers at the farthest edge of your desk are different. All 6 are tilted the same direction, 30 degrees down, as if a wind blew through from a window you cannot see, a window that might not even exist. That is what astronomers found at the edge of our solar system. 6 distant worlds, all leaning the same way, all pointing towards something invisible. The odds of this happening by chance are vanishingly small. When researchers first calculated the probability, they found it was 0.007%, less than 1/100%. Later analysis refined that number to roughly 1 in 250. Better odds, but still remarkably unlikely. How unlikely is 0.007%? Picture flipping a coin. Getting heads once is common. Getting heads twice in a row is less common. Getting heads 14 times in a row is extremely rare. That is what 0.007% feels like. 14 heads in a row, technically possible, but if you watched someone flip 14 heads, you would not assume luck. You would start examining the coin. Something is flipping the coin. Something out there has aligned these distant objects, pushed them, pulled them, guided them into formation over millions of years. The mathematics demands an explanation. Random chance cannot account for what we see. The most elegant explanation is gravity, a massive object far beyond the visible edge of our solar system, exerting its influence on everything that wanders close enough to feel its pull. A gravitational shepherd, invisible but present. Planet 9 acts like a sheepdog among these icy wanderers. Without a dog, sheep scatter. They drift wherever they please, following their own paths, spreading out across the hillside. But add a dog, and everything changes. The sheep cluster together. They move in formation. They respond to a force they cannot escape. The Kuiper Belt objects are the sheep, scattered across billions of miles of empty space, drifting through darkness that has lasted since the solar system was young. And yet, they cluster. They align. They respond to something. The dog is out there. We just cannot see it yet. This is not speculation dressed up as science. This is mathematics. Cold, precise, and demanding. When 6 objects in a vast empty region all tilt the same direction, probability forces us to ask why. When the odds against random alignment are 250 to 1, we cannot shrug and call it coincidence. The universe does not arrange itself this neatly without a reason. Extreme trans-Neptunian objects, that is what astronomers call these distant wanderers. Objects so far from the Sun that Neptune is practically their neighbor. They exist in a realm of permanent twilight, where our star is just another bright point among millions. And yet, they move in concert. They follow invisible instructions written in the language of gravity. Something is corralling them, something with enough mass to reach across billions of miles and whisper to their orbits. Not a violent force, not a sudden collision, just a gentle, persistent tug, year after year, century after century. For millions of years, something has been shaping their paths. The precision of this argument is what transforms it from interesting to compelling. Astronomers have not simply noticed a pattern and guessed at its cause. They have measured angles, calculated probabilities, tested alternative explanations, and found them wanting. Could it be Neptune's influence, somehow reaching farther than expected? The math says no. Neptune is too small and too close to produce these effects. Could it be a cluster of smaller objects working together? The math says no. The gravitational signature requires a single massive body. Could it simply be observation bias, where we only see certain objects because of where we point our telescopes? Researchers have tested this possibility and found it cannot explain the alignment. Each alternative falls away. The shepherd remains. This is how science works at its best, not wild guessing, not hopeful wishing, but careful elimination of possibilities until only one explanation survives. The clustering of those 6 distant objects is a message written in orbital mechanics, a message we are only now learning to read. And here is what makes this truly remarkable. We have done this before. We have used exactly this method, observing orbital anomalies and tracing them back to their source to find hidden planets. It worked once. It revealed a world that nobody had ever seen, simply by following the mathematics to its conclusion. That discovery changed our understanding of the solar system forever. It proved that gravity leaves fingerprints, that invisible objects can be found by the marks they leave on visible ones, that the universe rewards those patient enough to watch and calculate. The fingerprints are here again. Different location, different scale, but the same fundamental principle. Objects moving in ways they should not. Orbits tilting towards something unseen. Mathematics pointing toward the darkness and saying, look there, somewhere beyond the known, something waits. Not malevolent, not mysterious in any supernatural sense, just distant and dark and patient, circling the sun in an orbit so vast that human civilization might rise and fall a dozen times before it completes one lap. The sheep are clustered. The mathematics is clear. The gravitational sheepdog is out there, invisible against the black, doing what shepherds do, and we are getting closer to finding it. 64 light years from where you are right now, there is a world that looks like hope. It hangs in the darkness like a smooth blue marble, deep azure, serene, the kind of color that makes your chest ache with longing. From a distance, it could be a twin to our own pale blue dot, the shade of oceans, the promise of water, the suggestion of somewhere gentle. HD 189733b. Remember that name. It is the universe's cruelest bait and switch. That beautiful blue color comes from silicate particles suspended in the atmosphere, tiny fragments of glass catching starlight, the same blue that makes Earth look like a jewel from space, the same hue that astronauts describe with tears in their eyes when they look back at home. But here is what the color does not tell you. The surface temperature reaches 2400 degrees Fahrenheit. That is hot enough to melt aluminum, hot enough to soften steel, hot enough that the very concept of standing there becomes absurd. Your body would not burn. It would cease to exist as matter in any recognizable form. And the wind on this world moves at roughly 7 times the speed of sound. Imagine a hurricane. Now imagine that hurricane moving fast enough to cross North America in about half an hour. That is not weather. That is a weapon. That is the atmosphere itself becoming a blade. The glass in the sky does not fall like rain. It screams sideways, driven by those hypersonic winds. Molten silicate, still soft from the heat, shredded into razor fragments, and hurled across the planet faster than any bullet ever fired by human hands. A sandblaster running at jet engine speeds, a world that would shred you down to nothing before a single nerve could register pain. Standing on that surface would not hurt. You would not exist long enough to feel it. The universe is not calm, orderly, or safe. This world is the proof, not hidden away in some distant corner of the cosmos. not lurking in some violent galactic core, just 64 light years from your bedroom window, close enough that the light reaching your eyes left that world when your grandparents were young. And here is what makes it unbearable. The color lied. The blue that made astronomers gasp with wonder is the signature of the lethality itself. The glass that creates that beautiful azure shimmer is the same glass that rains sideways fast enough to strip metal from bone. The very thing that makes it look hospitable is the thing that makes it deadly. If you designed a trap for hope, you could not do better than this. Consider another world. TRES 2b. It orbits a star about 750 light-years away. This planet has a different trick. It reflects less than 1% of the light that hits it, less than coal, less than asphalt, less than fresh tar on a summer road. It is darker than any planet we have ever found. A black hole wearing a planet costume, a void with mass, something that drinks light and gives nothing back. If the blue marble is a trap dressed in beauty, this one does not bother with disguises. It simply absorbs everything and sits there in the dark, patient and absolute. These worlds prove something we need to understand. Visual beauty means nothing about habitability. The universe does not care about our hopes. It does not arrange itself to be welcoming. It does not soften its edges because we are looking. A world can shimmer like a sapphire and be worse than any hell ever imagined by human mythology. We search the cosmos with our telescopes, looking for anything that resembles home, and the cosmos shows us this: blue marbles that rain glass, dark spheres that eat light, worlds where the weather moves faster than sound and the temperature melts metal. Life survives despite the universe, not because of it. Earth is not typical. Earth is not the baseline. Earth is the exception so rare that we cannot calculate its probability. Every gentle sunset you have ever watched, every cool breeze on your skin, every morning you woke up and the air was breathable, and the ground was solid, and the sky did not shred you into fragments. That is luck. That is luck on a scale that defies comprehension. We live on a planet where water falls from the sky as water, where the wind moves at speeds a human can survive, where the temperature swings between limits that allow proteins to fold and cells to divide and minds to wonder about distant stars. None of that was guaranteed. None of it is common. The universe made billions of worlds, and most of them are variations on violence. Scorched wastelands, frozen tombs, pressure cookers, glass hurricanes, darkness so complete that light itself surrenders. And somehow, here, in this small corner of one spiral arm of one ordinary galaxy, the conditions aligned. Not perfectly, not comfortably, but enough for chemistry to become biology, enough for single cells to become forests and oceans full of fish and creatures that eventually stood upright and looked at the stars and asked questions. That is not destiny. That is not divine favor. That is the razor edge of probability tilting just slightly in our direction. The blue marble of death hangs 64 light-years away, beautiful and lethal, and we sit here on our own blue marble, one that happened to be gentle enough for life to take hold. Think about that the next time you complain about the weather. We have looked outward now. We have seen what waits beyond our small neighborhood, worlds that mock our hopes with their beauty, worlds that do not even bother pretending. The cosmic horror is real, and it is vast, and it fills the spaces between stars. But there is something closer to home that demands our attention. After all the distant nightmares, all the exoplanets and their impossible conditions, the greatest mystery might be right here, in our own solar system, beyond the last familiar planet, in the cold darkness where something massive waits, something we have been hunting for years, something the mathematics insists must exist, something that leaves fingerprints on the orbits of distant objects but refuses to show its face. The search continues, and we are getting closer. How do we even find these distant worlds? How do we know they exist at all? We cannot simply point a telescope at a star and see a planet circling it. The distances are too vast. The light is too faint. Stars are furnaces, blazing with the energy of nuclear fusion. Planets are tiny shadows beside them, reflecting only the faintest borrowed glow. Our exoplanet detection is like trying to understand an orchestra by listening through a wall. We hear the brass and percussion clearly. They are loud. They demand attention. But the subtle strings, the quiet woodwinds, they are there, somewhere, playing their parts. We just cannot make them out yet. The first method we use is called the transit method. We watch a star. We measure its brightness with extraordinary precision, and we wait. When a planet passes in front of that star, from our perspective, it blocks a tiny fraction of the light. The star dims, just barely. Then the planet continues its orbit, and the star brightens again. This works. We have found thousands of planets this way. But think about what this method favors. Large planets block more light. They create deeper dips, easier to spot. Planets close to their stars orbit faster. They pass in front of their stars more often. More transits means more chances to catch them. A planet like Earth, small and distant from its star, orbiting once per year. It crosses in front of its star once annually, barely dims the light at all. A hot gas giant hugging its star, swinging around every few days, blocking significant light each time. We see it immediately. The transit method hears the brass section loud and clear. The strings remain hidden. The second method is radial velocity. We do not watch for dimming. We watch for wobbling. When a planet orbits a star, it does not just get pulled by the star's gravity. It pulls back. The star wobbles slightly, tugged by the planet's mass. We can detect that wobble by measuring shifts in the star's light. Again, think about what this favors. Massive planets create bigger wobbles, easier to measure. Close-in planets orbit faster, creating more frequent tugs, more data points, better detection. A planet 10 times the mass of Earth, orbiting close to its star. We catch its signature relatively quickly. A planet the mass of Earth, orbiting at Earth's distance. The wobble it creates is so faint, so slow, that it gets lost in the noise. The radial velocity method hears the percussion section. The timpani strikes, the bass drums. The quiet flutter of a flute disappears. The third method is direct imaging. We try to photograph planets directly. No inference, no wobbles, no shadows, just light from the planet itself. This sounds straightforward. It is not. Finding an Earth twin is like trying to spot a firefly next to a lighthouse from across the country. The lighthouse drowns out everything. The glare of a star overwhelms the faint glow of any nearby planet. We can only photograph planets that orbit very far from their stars, where the glare is less blinding, and they need to be large and hot enough to emit their own infrared light. Otherwise, there is nothing to see. Direct imaging captures the outliers, the distant giants, the young, hot worlds still glowing from their formation. It cannot see small, temperate planets tucked in close to their stars. Those remain invisible. Every method we use has blind spots. Every technique selects for certain kinds of worlds. Let that settle for a moment. The extreme planets we have catalogued, the glass rain worlds, the tidally locked infernos, the darkness that devours light. They are not necessarily typical of all planets in the universe. They are the ones shouting loud enough for us to hear. It is like judging all ocean life by what washes up on beaches. You would find jellyfish, crabs, seaweed. You might conclude the ocean is full of things that crawl and sting and float on currents. And you would be right that those things exist, but you would miss the whales in the deep water, the fish in the open ocean, the creatures that never touch shore. Our surveys are biased, not because astronomers are careless, because physics works the way physics works. Some signals are easy to detect, some are buried in the background. The hot Jupiters we keep finding are not necessarily common. They might be rare oddities, sprinkled throughout the galaxy, but they scream their presence so loudly that we cannot miss them. Earth-like planets in Earth-like orbits are the hardest to detect. They whisper, and space is already so loud. This changes the picture we have been painting. The universe may not be dominated by hellscapes. We simply cannot see the gentle worlds yet. Our instruments improve every year. Our techniques grow more sensitive. The noise floor drops, bit by bit. One day, we will hear the strings, the woodwinds, the full symphony of planetary types that orbit other stars, not just the brass and percussion that currently deafen us. But here is the thing that matters for our search: the methods that struggle to find Earth twins in distant star systems. Those same limitations apply closer to home. Our own solar system has dark corners where something massive could hide. We have been looking with tools tuned for brightness and proximity. The outer solar system offers neither. Anything lurking beyond the known planets would be dim, cold, and moving slowly against the background stars. It would not transit anything. It would not wobble anything we could measure. And direct imaging of something that cold, that far, that dark, we might as well be looking for a shadow inside a cave at midnight. So astronomers have turned to a different kind of evidence. Not light, not wobbles. Something else entirely. They look at the objects we can see, the small icy bodies in the distant reaches, and ask a simple question: why do they move like that? If something massive is out there, it would tug on those distant objects. It would shape their paths. It would leave evidence written in their orbits. Invisible instructions carved into the movements of ice and rock. We have found those instructions. The orbits do not make sense without something pulling on them. The search continues, but now we know something important. The bias in our methods does not mean Earth-like worlds are rare. It means we have only been hearing part of the music, and the part we cannot yet hear might be the most beautiful movement of all. Something was wrong with Uranus. Not wrong in a dramatic way, not broken, just off, a subtle drift, year after year, pulling the planet away from where it should have been. Astronomers noticed. They measured. They double-checked their calculations. And still, the numbers refused to match. William Herschel had found Uranus in the late 1700s, a new world, the first planet discovered with a telescope. It was a triumph. Astronomers mapped its orbit carefully, tracked its slow journey around the sun. 84 years for a single lap. A human could be born, live an entire life, and die before Uranus completed one orbit. But as the decades passed, something became clear. Uranus was not following its predicted path. The deviation was small, tiny, really, the kind of thing you might dismiss as measurement error, except that it kept happening. Every year, the gap between where Uranus should be and where it actually was grew a little wider. The planet was being tugged, pulled. Something out there in the darkness was reaching across empty space and gently nudging Uranus off course. This is where the story gets strange. Because astronomers did not give up. They did not throw away their equations. Instead, they asked a question that seems almost arrogant in hindsight. If something is pulling on Uranus, can we figure out where that something must be, even though we have never seen it? Think about coming home to find your furniture rearranged, chairs shifted, table moved, books stacked differently. You never saw anyone enter. The door was locked, but you can look at what changed and deduce that someone was there. The evidence is in what got disturbed. That is exactly what happened with Uranus. Mathematicians looked at the wobble, the gentle deviation from the expected path, and worked backward. Pure equations. No telescope pointed at a suspect location, just paper, ink, and the laws of gravity. Imagine being so confident in your math that you tell the entire astronomical community, point your telescope at this exact spot in the sky, trust me. And then imagine being right. That kind of confidence is either genius or madness. In this case, it was genius. In 1846, astronomers turned their instruments toward a patch of sky they had never examined closely, a blank region of stars, unremarkable in every way. And there, exactly where the math predicted it would be, hung a new world. Neptune, a blue giant, cold and distant, 30 times farther from the sun than Earth. It had been hiding in plain sight for billions of years, invisible to human eyes, exerting its gravitational influence on everything around it. We found it not because we saw it first. We found it because we noticed its effects on something else. The precision still astonishes. Neptune was located within 1 degree of the predicted position. 1 degree. Hold your hand at arm's length and raise your thumb. It covers about 2 degrees of sky. Neptune was found within half that distance from where equations said it should be. No one had ever seen it through a telescope before that night. It had not been imaged, photographed, or detected in any way. Pure mathematics reached across the solar system and said, "Here, look here," and there it was. The mathematicians who found Neptune did something almost magical. They looked at the sky, saw something wrong with Uranus's path, and used pure equations to say, point your telescope exactly there, and you will find a new world. They were right. This is the method. This is the precedent. When orbits behave strangely, when objects drift from their predicted paths, when something invisible tugs on the things we can see, we can work backward. We can trace the disturbance to its source. We can find what hides in the dark. The discovery changed everything. It proved that gravity could reveal objects we had never seen. It showed that mathematics was not just a tool for describing the universe, but a tool for predicting what the universe must contain. Newton's equations were no longer just elegant formulas. They were a map to hidden treasures. For the first time in human history, a planet was discovered not by accident, not by patient scanning of the night sky, but by pure prediction. Someone did the math, announced a location, and the universe confirmed they were correct. Let that settle. We have been looking for Planet 9 with the same approach. The distant objects in the outer solar system cluster in ways that should not happen randomly. Their orbits tilt at angles that demand an explanation. Something massive lurks beyond Neptune, shaping their paths, herding them into alignment. We have seen this before. We have solved this puzzle before. Uranus wobbled, and we found Neptune. Now the distant objects wobble, and we search for something even larger, even farther, even more elusive. The parallel is not perfect. Nothing ever is, but the method remains. Watch what moves, measure how it drifts, calculate what must be pulling on it, and then look exactly where the math says to look. 1846 showed us this works. The equations can see what telescopes cannot. Mathematics can reach into the void and touch something real. The confidence required to make such a prediction seems reckless. To tell the world you know where an undiscovered planet must be, based only on calculations. To stake your reputation on numbers and gravity. Most people would hesitate. Most people would want more evidence first. But sometimes the evidence is the disturbance itself. Sometimes the clearest proof of something hidden is the way it pushes everything else around. Neptune was the proof of concept, the demonstration that orbital anomalies are not just noise, not just errors, not just problems to be averaged away. They are signals, messages written in the language of motion and mass. If you pay attention to what moves wrong, you can find what should not exist, or rather, what we did not know existed. The method worked spectacularly, so spectacularly, in fact, that astronomers immediately tried it again. They looked at other orbits, other wobbles, other deviations from prediction. They searched for more hidden worlds, more gravitational ghosts waiting to be revealed. Sometimes that confidence paid off, and sometimes it led them spectacularly, embarrassingly wrong. This is the story of a planet that never existed. The secret mathematician who helped find Neptune, the man who proved that gravity could reveal hidden worlds, spent the final years of his career hunting a ghost. Urbain Le Verrier had tasted triumph. He had pointed at empty darkness and said, "There is a planet there," and the universe had agreed with him. Neptune appeared exactly where he predicted. The world celebrated. Scientific journals overflowed with praise. So he tried again. Mercury troubled him. The closest planet to the Sun followed a path that did not quite match the predictions. Its orbit shifted in ways that Newton's laws could not fully explain. The discrepancy was tiny. Most astronomers dismissed it as measurement error, but Le Verrier knew better. He had seen this before. He had solved this puzzle before. There must be another planet. He named it Vulcan, Roman god of fire and forge, a world of eternal flame orbiting so close to the Sun that no human eye could see it against the glare. The theory placed Vulcan roughly 13 million miles from our star. Mercury sits about 28.5 million miles out. This phantom world would orbit even closer, baking in temperatures beyond imagination. Le Verrier calculated everything. Vulcan would complete one orbit in 19 days and 18 hours. Its path would tilt 12 degrees from Mercury's plane. He published the predictions. He announced the location. He told the world exactly where to look, and astronomers believed him. Why would they not? This was the man who found Neptune. This was the method that worked. Orbital anomalies revealed hidden worlds. Everyone knew that now. The search began. Imagine staring at a total solar eclipse. The moon slides across the face of the sun. For a few precious minutes, the blinding disk vanishes. Stars appear in the daytime sky. The corona blazes around the moon's shadow, and you are not watching the beauty. You are squinting at the darkness near the sun's edge, searching for a tiny dot that might be a planet. This is what they did for decades. Astronomers traveled to remote corners of the Earth. They hauled telescopes up mountains and across oceans. They waited years for the next total eclipse. They positioned themselves along the narrow path of totality, where the moon's shadow would sweep across the landscape for just a few minutes. Some damaged their eyes staring too close to the glare. Some spent their entire professional careers on this single hunt. All of them were looking for something that did not exist. The eclipses came and went. 1859, 1860, 1878. Each time, hopeful reports trickled in. Someone would claim a sighting. Someone would announce they had finally seen Vulcan cross the solar disk. The scientific community would hold its breath. Then other astronomers would analyze the data. The sighting would dissolve into error, a misidentified sunspot, a smudge on the telescope lens, a star mistaken for a planet. No Vulcan. Leverrier died in 1877, still convinced his planet existed. He never stopped believing. The same stubborn certainty that led him to Neptune dragged him to his grave chasing a phantom. His successors continued the search. They could not let go. The method was sound. The math was correct. The planet had to be there. Entire careers evaporated into those eclipse expeditions. Astronomers who might have discovered real worlds spent their productive years waiting for a ghost that would never appear. The scientific community clung to Vulcan because abandoning it meant admitting something else was wrong. Not the telescopes, not the observations, something deeper. Maybe the math itself was incomplete. The answer came from an unexpected direction. A young physicist working in a Swiss patent office had been thinking about gravity, not as a force that pulls objects together, but as something stranger, something that bends the fabric of existence itself. Albert Einstein did not find Vulcan. He made it unnecessary. General relativity described gravity as the curving of space-time. Massive objects warp the emptiness around them. The sun, with nearly all the mass in our solar system, bends space so severely that anything orbiting close to it follows a slightly different path than Newton predicted. Mercury's strange orbit was not caused by a hidden planet. It was caused by curved space. The anomaly came from warped geometry, not unseen mass. Vulcan was never there because nothing needed to be there. The equations were incomplete, not the observations. Think about searching your house for a burglar. Furniture has moved. Pictures hang crooked on the walls. Doors stand slightly open. Every sign points to an intruder. You check every closet. You look under every bed. You spend years convinced someone is hiding in the shadows. Then one day you realize the house was built on uneven ground. The foundation shifted. The floor tilted. Everything moved because the structure itself warped, not because anyone broke in. There was never a burglar. There was only a crooked floor you did not know about. That is what happened with Vulcan. Astronomers searched for a planet causing disturbances when the disturbances came from space-time itself. The tragedy lingers. Decades of eclipse watching. Thousands of hours staring at the sun's edge. Careers devoted to a world that existed only in equations. Not because anyone made a mistake, because the universe operated by rules they had not yet discovered. The same methodology that revealed Neptune produced nothing here. Orbital anomalies can point toward hidden planets. They can also point toward hidden physics. The challenge is knowing which. Planet 9 sits at the other end of our solar system. Different location, different evidence, different math. The distant objects in the outer darkness cluster in ways that demand explanation. Their tilted paths cannot be blamed on curved space-time. The anomalies are gravitational, not relativistic. Something massive shapes their orbits. We learned from Vulcan. We learned that confidence must be tempered with humility. We learned that the universe can fool us in ways we never expected. But we also learned to recognize the difference between missing planets and missing physics. Mercury orbits close to the Sun, where space-time curves most severely. The outer solar system stretches so far from our star that relativistic effects become negligible. Out there, when orbits behave strangely, the explanation is almost certainly gravitational. Something is pulling, something is herding, something waits in the darkness. The ghost planet Vulcan haunted astronomy for half a century. It consumed brilliant minds and wasted precious years. But its absence taught us something valuable. Not every wobble means a world. Sometimes the rules themselves need rewriting. And sometimes, in the cold emptiness beyond Neptune, the wobble really does mean a world. Sometimes the answer is not a missing world. Sometimes the answer is a world that was never allowed to exist. Between Mars and Jupiter, a vast ring of rock drifts through the darkness, the asteroid belt. For over a century, astronomers believed they knew its origin. A planet had once orbited there, something ancient, something whole, and then, somehow, it shattered into a billion fragments. They called this phantom world Phaeton. The story seemed to fit. In 1801, an Italian astronomer named Giuseppe Piazzi pointed his telescope at the gap between Mars and Jupiter. He found a small, rocky body. He named it Ceres. The following year, Heinrich Olbers discovered another. He called it Pallas. Two objects orbiting in nearly the same region. Then more appeared, and more. Too many to be coincidence. Astronomers in the 1800s looked at all those tumbling rocks and reached what seemed like an obvious conclusion. These were pieces of something larger, something that had been destroyed. The fragments scattered across space like shrapnel frozen in time. Picture a shattered vase lying on the floor. Your first instinct is to assume it was whole once. An earthquake, perhaps. A careless elbow. Something broke it. That is how scientists viewed the asteroid belt. They saw the pieces and imagined the disaster that created them. The Phaeton theory held for generations. A planet-sized world, torn apart by some catastrophic force. Maybe it collided with another object. Maybe its own internal stresses ripped it to pieces. The details remained fuzzy, but the core idea felt solid. The belt was debris, wreckage, a graveyard. It was a beautiful explanation. It was also wrong. The vase was never assembled in the first place. Consider the four largest objects in the asteroid belt: Ceres, Vesta, Pallas, Hygeia. These four alone account for half the total mass of everything orbiting in that region. Half. Let that image settle. Countless thousands of rocks, and just four of them hold as much material as all the others combined. If Phaeton had truly been a planet, those four objects should be roughly similar. Fragments of the same world, sharing the same composition, the same history. But they are nothing alike. Ceres is rich in water ice and clay minerals. Vesta is volcanic rock, baked by ancient internal heat. Their chemistries tell completely different stories. They did not come from the same parent body. They never touched each other. They never touched anything. The asteroid belt is not debris from a destroyed world. It is the blueprints for a world that was never allowed to be built. 75% of asteroids in the belt are carbon-based, primitive, unchanged since the earliest days of the solar system. 17% are silicon and stone. The rest are metal, iron, and nickel cores that never found a body to wrap around. These are the raw ingredients of planet formation, the same stuff that built Earth and Mars and Venus. They should have clumped together. Gravity should have pulled them into larger and larger masses until a planet emerged from the chaos. That is how every other rocky world formed. But something stopped the process here. Jupiter, the largest planet in our solar system, sits just beyond the asteroid belt. Its gravity reaches across millions of miles, tugging at everything nearby. When the solar system was young, this region held far more material than it does today. Enough rock and dust and ice to build something substantial. Maybe not an Earth, but something. Jupiter would not allow it. Every time particles began to gather, Jupiter's gravitational pull yanked them apart. Every time a protoplanet started to form, the giant planet's influence scattered its building blocks like seeds blown from a dandelion. The belt was not destroyed. It was prevented, interrupted, denied. Imagine a bully at a playground. bigger than everyone else. Other children try to build sandcastles, gathering handfuls of sand, shaping walls and towers. But the bully keeps kicking through their work before it takes shape. Not once, not twice. Every single time, for millions of years, the sand is still there. It just never becomes a castle. That is what Jupiter did to the asteroid belt. 99.99% of the original mass in that region vanished in the first 100 million years. Not vanished into nothing, scattered, flung into the inner solar system, ejected into the outer darkness, swallowed by the sun, or consumed by other planets. Almost everything that once orbited between Mars and Jupiter is gone now. What remains is a thin residue, a ghost of what could have been. The Phaeton theory made intuitive sense. When you see broken pieces, you assume something broke. When you see fragments, you imagine a whole that shattered. But the universe does not owe us intuition. Sometimes the pieces were never together. Sometimes nothing broke because nothing was ever built. Scientists spent decades searching for evidence of Phaeton's existence. They analyzed asteroid compositions, looking for shared origins. They calculated orbital paths, trying to trace the fragments back to a common source. They found no evidence. The math did not work. The chemistry did not match. Phaeton was a story we told ourselves because we needed an explanation for the mess. The real explanation is quieter, less dramatic, more true. There is another myth that needs correcting. Every science fiction movie shows the same thing. A spacecraft approaches the asteroid belt. Alarms blare. The pilot grips the controls. Rocks tumble past the viewport in terrifying density, missing the hull by inches. The hero weaves and dodges through an impossible gauntlet of stone. It makes for good cinema. It has nothing to do with reality. In 1972, NASA's Pioneer 10 became the first spacecraft to cross the asteroid belt. Controllers held their breath as the probe entered the region. They expected difficulties. They had calculated the risks carefully, prepared for the possibility of collision. Pioneer 10 sailed through without incident. Nothing came close. The rocks in the asteroid belt are separated by millions of miles. Millions. Picture a football field. Now imagine scattering 3 or 4 grains of sand across its entire surface. That is the density of the asteroid belt. The emptiness between objects is so vast that collision is nearly impossible. You would have to aim for an asteroid to hit one. Every probe since Pioneer 10 has crossed the belt safely. Voyager, Galileo, Cassini, New Horizons. None of them even bothered to dodge. There was nothing to dodge. The belt is not a barrier. It is barely an obstacle. It is empty space with a few rocks floating through it, so far apart that they might as well exist in separate universes. Phaeton was never there. The destruction never happened. The danger was never real. The asteroid belt is just leftover construction material, unused, abandoned, scattered by a planet so massive it would not share the neighborhood. Jupiter stood guard for 4.5 billion years, refusing to let anything else grow in its shadow. Some worlds are destroyed. Some worlds are never allowed to be born. The difference matters. The solar system holds many mysteries, objects that should not exist, orbits that should not be possible, patterns that demand explanation. Some of those mysteries have simple answers hiding in plain sight. Others point towards something genuinely unseen. The asteroid belt taught us an important lesson. Our instincts can mislead us. The obvious explanation is not always correct. Sometimes we invent planets to explain debris when the debris was never a planet at all. But sometimes, when we trace the evidence carefully, when we follow the mathematics wherever it leads, we find that something truly is hiding in the darkness. Something real. Something waiting to be discovered. The trick is knowing which mystery is which. Consider Jupiter. You know Jupiter, the giant, the king, a ball of swirling clouds larger than 1,000 Earths. You have seen the photographs. The red spot, the banded atmosphere, the storms that dwarf continents. But those images show only the surface. They show only what we can see. Beneath those clouds lies something stranger than any science fiction writer imagined. Hydrogen. Simple hydrogen. The lightest element in the universe. The stuff that fills party balloons. The fuel that powers stars. On Earth, hydrogen is a gas, invisible, weightless. It floats away if you do not contain it. But on Jupiter, something different happens. Something that should not be possible. Dive beneath those swirling clouds. Keep going. Pass through layers of atmosphere thicker than any ocean on Earth. The pressure builds. It doubles, triples, multiplies beyond anything you have experienced. Keep descending. The hydrogen around you begins to change. It is no longer a gas. It is no longer behaving the way hydrogen should behave. The pressure becomes so immense that hydrogen forgets what it is. The atoms squeeze together so tightly that electrons break free from their nuclei. They flow between atoms like water through sand. The hydrogen becomes metal, not solid metal, not frozen metal, liquid metal, a flowing, conducting, shimmering ocean of metallic hydrogen, 25,000 miles deep. Let that number settle, 25,000 miles. The entire diameter of Earth is 8,000 miles. You could stack 3 Earths inside this ocean and still have room to spare. An ocean 3 Earths deep, made entirely of the lightest element in existence, transformed by pressure into something that conducts electricity like copper wire, but flows like water through a river. No human will ever see it. No probe will ever survive the journey down. We know it exists only because the math tells us it must. Jupiter's magnetic field is too powerful to be explained any other way. Something beneath those clouds is conducting electricity on a scale we can barely comprehend. The metallic hydrogen ocean generates a magnetic field that stretches halfway to Saturn, the lightest element in the universe, crushed until it becomes liquid metal. Jupiter keeps this secret hidden beneath beauty. We look at the photographs and see storms and colors. We do not see the impossible ocean beneath. We do not see the physics pushed beyond breaking. We think we understand the giant planets because we have seen their faces. We have seen almost nothing. And then there is Mars. Mars feels familiar. We have sent rovers. We have photographed every crater. We have mapped the ancient riverbeds and dreamed of colonies. Mars is the planet we know best, after our own. Mars is the planet we plan to visit. Mars is the planet we have studied for decades, with robots crawling across its rust-colored surface. Here is a mystery we cannot solve yet. Mars has methane in its atmosphere. Sometimes it appears, then it disappears. We do not know what is making it. We do not know what is destroying it. Could there be cows on Mars? Probably not. But honestly, we do not know what the answer is. That is the truth. Methane should not exist on Mars. The Martian atmosphere is thin and exposed. Sunlight and chemical reactions should break methane apart within a few centuries. Every molecule of methane we detect should have been destroyed long ago. Yet there it is, appearing in plumes, vanishing weeks later, coming back in different locations. Something on Mars is producing methane right now, not millions of years ago, not in the ancient past, now, today. While you listen to these words, something on that cold red world is releasing gas into the thin Martian air. The source could be geological. Deep beneath the surface, chemical reactions between water and rock can produce methane without any life involved. Hot springs and volcanic vents on Earth release methane this way. Perhaps Mars still holds pockets of geothermal activity, hidden chambers where ancient heat drives ancient chemistry. The source could be biological. On Earth, the vast majority of atmospheric methane comes from living things. Bacteria in swamps, microbes in the guts of animals, decomposing plants in wetlands. Life makes methane. Life makes enormous amounts of methane. When we detect methane on another world, we cannot help but wonder. Scientists have joked about cows on Mars. They are not serious, but the joke hides a real question. If something is producing methane, and that something is not geology, then what? Microbes? Bacterial colonies hidden beneath the permafrost? Ancient life that never quite died out? We do not know. The methane appears and vanishes too quickly. We cannot track it to its source. We cannot explain why it disappears so fast. Our models of Martian chemistry cannot account for the rapid destruction. Something is happening on Mars that our science has not yet described. The nearest planet we can almost reach. The world we have studied more than any other. And it holds a mystery we cannot solve. The Sun itself contains 99.86% of all the mass in our solar system. Everything else, every planet, every moon, every asteroid and comet, all of it together amounts to a rounding error. Jupiter and its impossible ocean, Mars and its mysterious breath, Earth and everything we love, all of it combined does not equal 1% of the solar system. We live in the scraps. We inhabit the leftovers. The Sun does not notice us. It burns, and we exist in its shadow, trying to understand the crumbs it left behind. Even here, even in our own backyard, the mysteries multiply faster than our answers. We build telescopes to see across billions of light years. We search for planets around distant stars. We wonder if life exists in other galaxies. But the world next door holds secrets we have not cracked. The metallic ocean beneath Jupiter's clouds, the methane breathing in and out of Mars. These are not distant puzzles. These are our neighbors, our cosmic family, the planets we named after gods because we thought we understood them. We understand so little. And perhaps that is the point. Perhaps the universe keeps reminding us that knowledge is a journey, not a destination. We solve one mystery and discover 3 more hiding behind it. We answer one question and find ourselves asking 10 we never thought to ask. The solar system is not a museum. It is not a collection of facts waiting to be catalogued. It is alive with strangeness, breathing with questions, holding secrets in places we thought we had mapped completely. Jupiter hides an ocean of liquid metal made from the lightest substance we know. Mars exhales gas that nothing should be making, and nothing should be destroying so quickly. These are not distant abstractions. These are worlds we can see in the night sky with our own eyes, close enough to touch, strange enough to humble us. We have traveled far together, from the hidden edges of our own solar system, where something massive waits in the dark, through frozen wastelands orbiting distant suns, past worlds locked between twin stars, pulled in directions that should have torn them apart long ago. We stood on the surfaces of magma furnaces where rock itself becomes weather. We watched glass fall sideways through alien skies at speeds that would shatter anything we have ever built. We learned that the same mathematics that revealed Neptune to waiting telescopes failed completely when it predicted Vulcan, a planet that never was, a ghost born from incomplete understanding. And we learned that the rubble drifting between Mars and Jupiter tells a different story than we once believed. Not wreckage, not the bones of a shattered world, just blueprints for something that was never permitted to exist. The universe does not follow the rules we wrote for it. We drew lines around stars and called them habitable zones. We imagined water pooling on rocky surfaces, atmospheres holding warmth against the cold. We built our expectations on the foundation of what we know here, on this small world, in this unremarkable corner of one ordinary galaxy. And the universe responded by showing us worlds that mock those expectations, planets that exist where physics says they should not, conditions so extreme our models simply cannot accommodate them. The universe is not calm, it is not orderly, it is not safe, and yet something remarkable is happening. Our instruments grow sharper with each passing year, our archives deepen, our models improve. The same observatories that once searched for shadows now prepare to capture light so faint it would take 40 years of work just to confirm a single distant wanderer. The Vera Rubin Observatory is nearly ready. Its mirrors will sweep the southern sky with patience we cannot match. Its cameras will record the slow movements of objects so distant that their orbital periods stretch across human civilizations. If something lurks out there in the frozen dark, hiding at distances that dwarf everything we have measured before, we may finally see it. Planet 9 might be found within our lifetimes, not because we are lucky, because we learned, because every failed hunt taught us something, because Vulcan's absence revealed the curvature of space itself, because the aligned orbits of distant ice worlds pointed towards something we had missed, because we kept looking even when the darkness seemed complete. Earth is not typical. Earth is lucky. We spin through a cosmos filled with violence and extremes, and somehow this fragile world gathered an atmosphere that does not crush us, oceans that do not boil, a magnetic field that shields us from radiation that would sterilize our surface in hours. We are not the center of anything. We are not the template. We are the exception. And from this exception, we have learned to see beyond ourselves. The search for Planet 9 is more than astronomy. It is a reminder that the darkness between worlds still holds secrets, that humility and curiosity walk together, that every answer we find carries new questions in its shadow. We may never stand on its surface. We may never send a probe to photograph its frozen plains, but knowing it exists would change how we understand our own origins, where we came from, what forces shaped the orbits of everything we call home. The sky is vast, the dark is deep, and we are getting better at seeing.